Imagine tracking a fluctuating sequence of random events, like a stock price or a sequence of scientific experiments. In probability theory, we use martingales to model these fair games, and we rely on concentration inequalities to guarantee they won't cross certain safety thresholds. However, classical proofs for these bounds share a hidden flaw. They routinely discard information by dropping non-negative terms to make the math work. This paper introduces a revolutionary path-space calculus that accounts for this lost information exactly. By treating these inequalities as exact identities, we can finally measure precisely what classical bounds throw away. To see this information loss in action, let's examine the 4 distinct residuals visualized on page 2 of the paper. Each classical inequality leaves behind a specific type of slack that this new calculus can name and measure. For PAC-Bayes bounds, the slack is the divergence to a running Gibbs tilt. For sequential tests, evaluating a martingale at its running maximum incurs a peaking penalty due to anticipation. In Doob's maximal inequality, we find an unspent budget that vanishes only in the limit. Finally, when pooling multiple tests, we gain a coincidence boost from model disagreement. All 4 of these residuals are measured in a common currency, information nats. At the core of this mathematical breakthrough is a single, master entropic identity that sits at the peak of a free energy landscape. As shown in Figure 3, when we look at the variational objective of energy minus information cost, it is unimodal and reaches its maximum exactly at the Gibbs tilt. For an exact conditional log cumulant generating function, the log expectation of the normalized exponential martingale is pinned at 0. When we replace this exact cumulant with a computable majorant, we step down from this peak. The amount we step down is the exact cumulant gap, which widens our confidence bands, but can now be fully quantified. This master identity allows us to systematically recover and sharpen a wide range of classical concentration inequalities. By specializing the entropic inequality to different cumulant majorants, we can derive Ville's inequality, the Azuma-Hoeffding bound, and PAC-Bayes formulas from a single source. For instance, Ville's first passage inequality is revealed to be a relative entropy equality where the residual is the mean overshoot at first passage. Instead of proving each of these bounds using ad hoc, isolated arguments, we can now view them as simple relaxations of the same underlying path space identity. While entropic methods work beautifully for exponential moments, Doob's classical LP maximal inequality requires a completely different approach. It resists entropic analysis because its natural extremal is a vanishing martingale with a Pareto distributed maximum, causing the entropy ratio to degenerate. To solve this, the author moves to a power mean geometry. Here, the role of the Gibbs tilt is played by a family of concave certificate functions. By analyzing these certificates step by step, the unspent budget of Doob's inequality is resolved into 3 clean, non-negative pieces: a holder deficit, an optional stopping deficit, and an initial value. Moving beyond single processes, the path space calculus reveals a massive benefit when we pool multiple sequential tests together. If we have several bettors wagering against a null hypothesis, their individual disagreements actually provide valuable evidence. By taking a geometric mixture of these test martingales, we create a supermartingale. The Ville bound for this mixture is tightened by a multi-way coincidence divergence, which represents the accumulated disagreement among the bettors. This means that model disagreement dynamically sheds mass, allowing us to construct much tighter and safer sequential tests than classical theory would suggest. Perhaps the most profound extension of this theory is how it handles the act of peeking at data at arbitrary, unplanned times. If an analyst decides when to stop and look based on the trajectory itself, they introduce optional stopping bias. The path space calculus quantifies this bias exactly by introducing an anticipation martingale and a hazard clock for any random time. On a joint path time space, choosing when to look adds a single extra factor to our identity: the peaking penalty. This penalty is exactly 0 for stopping times, but can become infinite for fully anticipatory times that look into the future. To bridge the gap between theory and practice, the author conducted rigorous empirical evaluations of these identities. As shown in Figure 8, When we sweep the time horizon, the first passage deficit of Ville's inequality remains completely unchanged. However, when we refine the step size of our discrete process, the deficit vanishes as a power law. This confirms that the overshoot at the boundary is the primary source of slack in discrete time, and that the process approaches the continuous path Pareto limit as the step size goes to zero. The paper also demonstrates these tight bounds on deep neural networks. While this framework provides an elegant unification, several key challenges remain for future research. First, the exact overshoot calculations depend heavily on the specific increment distribution, meaning we cannot easily write a universal closed-form residual for all discrete processes. Second, when applying PAC-Bayes bounds to deep neural networks, the tightness of our safety certificates is highly sensitive to the choice of the prior anchor. An uninformed prior can easily lead to vacuous bounds, meaning that the practical utility of these exact identities still depends on our ability to choose smart, data-independent priors. In conclusion, this paper fundamentally changes how we view sequential probability. By replacing one-sided inequalities with exact path space identities, we can now treat information as a physical quantity that is conserved and tracked. Whether we are designing safe anytime valid tests, pooling diverse machine learning models, or trying to understand the exact cost of peeking at our data, this unified calculus provides the mathematical tools to measure what was once discarded. It opens up exciting new pathways for both theoretical probability and practical, data-safe machine learning.